Okay, so let me try to get this. Okay. I wonder what happens if I do switch to tab. Does that do anything? Let's see. Okay, so today we are going to be talking about. Well, okay, so let's review very quickly what we had talked about before. So we've been looking at first order ODEs so far, and these are ODEs that can be written in the form y prime is a function of x and y. And we looked at a couple of easy cases to solve for this. The easiest was when y prime, this is just a function of x, right? And so in this case, we just integrate. We just integrate both sides. We think of y as a function of x, and the derivative of y is also a function of x. So all we have to do is find the antiderivative. Okay, so that was the easiest case. The next easiest case was when we had y prime as a function of y, right? And so we kind of cheated a little bit by writing this in Leibniz notation. So we would write this dy dx equal to g of y. And then we did a kind of a little bit of a trick, which was that we just treated this dy dx as if it was a fraction. And we rewrote this as 1 over g of y dy equals dx, right? And we just integrated both sides. So now we get on one side, let's call this antiderivative h of y. And on this side, we get x of y plus some constant. And then we solve for y to get the solution. Right? Now, we didn't talk about this that day, but what happens if we get into a situation where we can't solve for y? So if we can't solve for y, to get y as a function of x, then we can typically leave as is, and we call this an implicit solution. So things that satisfy the x in terms of y that we get here. This we'll just think of this as, we'll move the c over to the other side. So we get some function x in terms of y, and we think of this as we've solved for y implicitly. Anything that's true of a solution of this differential equation will be true if we plug it in here for y for whatever x value. Okay. So it doesn't give us an explicit solution, it gives us an implicit solution. So as opposed to explicit, which is what we would prefer. Okay, so these were a couple of easy cases for these first order ODEs. Okay, let's scroll it off completely yet. Okay, today we're going to introduce a broader kind of first order ODE that includes both of these cases. So framework that includes and extends both of these cases, and these are called separable ODEs. Okay, what is a separable ODE? It is an ordinary differential equation that can written y prime is equal to f of x g of y. Okay, so ordinarily what we have here is y prime is equal to something that's a function of x and y. And what this does, or what we can do with the separable ODE, is we can take that function of x and y and we can factor it into two factors. One factor that depends totally on x, and one factor that depends totally on y. So rewriting in this form is referred to as called it's called a separation of variables. So if we take an ODE and we write it like this, it's called a separation of variables. Now, the first thing I'll note about writing things in this form is that it allows us to very easily check the hypotheses of the existence and uniqueness theorem. So the existence and uniqueness theorem, what were the conditions for that to apply? Well, first, f of x, y is continuous, and the partial derivative of f with respect to y is continuous. And both of these are in some region around the point x0, y0. So our initial point, our initial condition. So we needed both of these things to be true. And this is particularly easy to check if we have our ODE in separable form. So it's if we've separated the variables. Okay, so first of all, we have all of the parts that depend on y separated out as their own factor. And so it's easy to check if the partial derivative of this whole function on the right is the partial derivative with respect to y is continuous. We just look at is g prime of y, g prime of y continuous. We, if it's in order to get the derivative of it, has to be differentiable. And in order to be differentiable, it has to be continuous. So we just, if we can take the derivative, and if that derivative is continuous, then we've satisfied this condition right here. And then all we need to know is if this whole function is continuous. So next we ask, is f of x continuous? And if it is, then we have a continuous function multiplied by a continuous function So the whole thing is, so it's much easier to check in this case if the hypotheses of the existence apply. And of course, if they do, we have a unique solution which exists somewhere around our initial condition. Okay, so that's one of the benefits of a separable ODE. Okay, I'm going to pause right here and see if anybody has any questions at this point. Everything good so far? Now, let's look at some examples of separable ODEs. So these original easy ones that we had, these are separable ODEs. So when we had y prime is just a function of x, then we had that our g of x is just 1. So this is already written in form of a separable equation. The other function there is 1. Similarly, y prime equals g of y. In this case, f of x is just equal to 1. So we can write that as a separable ODE as well. So it includes all of those cases we've already talked about. Includes some other stuff as well. A lot of other stuff. So y prime is equal to 2xy. Here we can take f of x to be 2x, for example. G of y, 1. So we could probably just do something like that to demonstrate that this is separable. Okay. Y prime is equal to e to the x plus y. Is this a separable ODE or not? I'm going to write this as a product of something just in terms of x, something in terms of y.
Yes.
I agree. So how do you write this as a product? Was that Tyler?
Yeah, e to the x times e to the y.
This is just a review of what would be algebra 2, maybe. Okay. So in this case, f of x is e to the x of y is e to, I'm sorry, cube. Okay. Y prime is equal to x plus y. Separable? Actually, just go ahead and say, actually, I want to change the view. Okay. This is not separable. So x plus y cannot be written as some function of x times some function of y. Okay, so this is an example of an ODE that is not separable, a first order ODE is not separable. So unfortunately, this doesn't work for everything. Okay, what about this one? One plus x squared plus y squared plus x squared y squared. Is this separable? very early. Some people are still waking up, myself included.
I want to say yes because it could be written in the form of like factoring it into 1 plus x squared and 1 plus y squared.
Yeah, exactly. That's perfect. So we can write it like this. And yeah, as Sean pointed out, the product of something just in terms of x, something just in terms of y. So this. Okay. Now, we've seen some examples of separable ODEs. Maybe you saw one example of one that's not separable. How can we deal with these things? So there's a really nice way of dealing with separable ODEs. So let's start off by saying we have y prime is equal to f of x, g of y, and let's rewrite this as 1 over g of y times y prime is equal to f of x. So I'm going to introduce a new function, h of y is equal to 1 over g of y. And so now I can rewrite this thing as h of y, y prime is equal to f of x. This is just for our convenience. So we can think of this as a function of y. Now, let's let h of y, f of x be anti-derivatives of h of y and f of x, respectively. In other words, we can write h prime of y is equal to h of y and f prime of x equal to f of x. Okay, if we now think of y as a function of x, so in other words, y of x, then if we take h of y of x and we take its derivative with respect to x. So we're thinking of y as a solution to this ODE, right? Solution will be a function of x. So y will be a function of x. So was there a question? So we apply the chain rule here. We get that this is h prime of y of x multiplied by y prime of x. And so this is just h of y times y of x. Now, we can use this to rewrite, where is it, back here, h of y times y prime of x Oh, sorry, I left the prime out there. Okay. So we can write this now as derivative with respect to x of y, h of y of x. So that's this side. And then we'll write the other side as the derivative with respect to x of capital F of x. So now we've just rewritten this thing as this. And by the fundamental theorem of calculus, or by integrating both sides, we get h of y of x is equal to f of x plus some. All the primes are gone. We just have y, the function y, buried some here inside the function h. What we will do is solve for y. Or at least attempt to. And once again, if we can't solve for y, sometimes it's very difficult, sometimes it's just straight up impossible. If we can't solve for y, then we have just simply an implicit solution. So I'm actually gonna leave all this on the screen so that anybody's still right. Okay. Are there any questions about this general idea? So what we've done is we've shown that we can take a separable ODE and we can find at least an implicit solution, sometimes an explicit solution, using this method. Right? All it involved was finding the antiderivative. Remember, this was 1 over g of y. So all we had to do was find an antiderivative of f of x and an antiderivative of 1 over g of y. We call this h of y. So fairly straightforward things that we can do in terms of the calculus that we already. Okay, now all of this puts, actually, I do have to say one thing about this. At a certain point, we were integrating one over g of y. And remember from, I guess, Calc 2 or Calc 1, whenever we talked about integration, this was always of a continuous function, right? And so if g of y equals 0, or let's say let's write it like this, g of y 0 is equal to 0. For some y0, then 1 over g of y is not continuous, right? It has a discontinuity right there at y is equal to y0. So we have to deal with this situation, first of all, of whenever we have g of y has some value that we can plug in and get 0. So if that's a possibility, we should deal with that. And fortunately, that's very easy to deal with. So you remember we're looking at y prime is equal to f of x, g of y. And if we have g of y0 is equal to 0, then we have y prime is f of x, g of y0 equal to of x times 0, which is just 0. And what is this telling us at this point? Y prime is equal to 0, right? The derivative of y is equal to 0, which means the value of y does not change. In other words, y of x is equal to some constant. In fact, we know what the constant is. Constant is y0. So if this solution passes through this point y0, or if it passes through the y value y0, then I apologize for this tablet. If our solution passes through this y value y0, then we know it's y value everywhere else because the derivative at that point, the change in the y value is 0. And so we call these stationary or we call this a stationary solution or an equilibrium solution for obvious reasons. So the first thing we'll do is, well, this is easy to find, just solve g of y is equal to 0, or at least, this is just a root finding problem now. We're just figuring out when g of y is equal to 0. And then we can apply all of the stuff that we've just said about finding antiderivatives. So now everything is valid. We know that for other solutions, g of y doesn't pass through 0, and so these are non-stationary solutions. So then we find the other solutions by integration and maybe solving for y. Give everyone who's writing a second. Yep. Okay, so like I talked about in a previous class, this is all of this work is, this is for the sake of putting our calculations on a firm foundation. But there's an easier way to remember this. And if we look back at, if we can do this, shrink and go back to here, where I said we were doing this kind of trick. We were cheating a little bit. We're treating dy dx as a fraction when it's, well, not, I mean, it's debatable whether or not it's actually a fraction, but certainly the people who invented calculus did think of this as a fraction. And people worried that this was somehow paradoxical or nonsensical. And so a lot of work went into putting all of these things. Excuse me, just a second. All right, I apologize for that. A lot of people did a lot of work putting calculus on a firm foundation. That's the point of what I was saying. Put this back to normal size. Okay. And we're the beneficiaries of all of that work. But now we can go back and look at how we treat these things, like sometimes like fractions, which we did in that one of those special cases of the separable equations. And we'll just do that. We'll just do that for separable ODEs in general. Okay. So there was all of the work. There was all of the difficult way of thinking about it in terms of the chain rule and all of that. Now we'll do it the easy way. So we have y prime is equal to f of x, d of y. And we'll rewrite y prime in Leibniz notation, named after one of the inventors. So we write this as dy dx. That's that fraction form, equals f of x, d of y. And now we're going to treat dy dx as if it's a fraction. So we rewrite this thing as dividing the g of y over to the other side and multiplying the dx over to the other side, treating them just like they're just ordinary real numbers, which they are not. They definitely are not, but we're going to treat them like they are anyway. And then we just integrate both sides. And maybe throw in a plus c just to be on the safe side. And what you see is we get the exact same solution that we did by chasing this down all the way through the chain rule and making sure that we were being rigorous about all of our reasoning. Okay, now that we've done all of that and we've convinced ourselves that everything is on a good foundation, we'll just go back to doing things the way Newton and Leibniz did them. Gives you kind of a hint of how these guys at the beginning of mathematician made so much progress so quickly. They were kind of cheating. They didn't have to think about the hard details. It's a little bit of an exaggeration, but not by too much. So this is a shorthand way to think about these problems, and it works perfectly well. So we're going to go with it. Okay, so we've got about 20 minutes left, 24 minutes. The rest of this time we'll do examples. So what's the first example? Let's go back to the first example, the first example that wasn't one of the ones that we'd already looked at before. Actually, let's look at an example that we have looked at before. So this uses different variables. So this is known as Newton's cooling law. And it basically says that this is T is temperature. And T0 is the temperature of, this is the temperature of something, of the thing that we care about. This is the temperature of everything else. So this is a hot mug of coffee in a room temperature room. So this T0 here is the room temperature, the T is the temperature of the coffee. And the rate at which it cools is proportional to the difference between the two temperatures. So if it's a really hot cup, it cools more quickly than a cup that's pretty close to the temperature of the room already. Now, if it's a cold beverage, then this could be called Newton's warming law instead. So, how can we analyze this thing? Well, first of all, we know that we'll think of our f of, let's say our f of x just equal to 1. Right, this one, there's no x involved. There's no independent variable involved in this equation. This k is a constant, the proportionality constant. And our solution, t of x, actually we'll think of our independent variable. This is happening through time. Call it t. And so there's a lowercase t and a capital T, and this is the our solution. And so remember, whenever we are looking at our function of the dependent variable, this will be our g of t and our f of t. Well, we already have that. We wrote that. Our f of t is just 1. So this is a separable equation. It's one of those easy ones, but we'll just use it as an example of looking, first of all, for stationary solutions. So in this case, we want to find g of t is equal to 0. So that's t minus t0. And so there's an obvious solution there. So this right here, t is equal to t0, the stationary solution. Well, this is an obvious one. This is when the thing that you're drinking is already exactly at room temperature, and so the temperature doesn't change. Okay. Now we can solve this thing. We'll write d t capital T and lowercase equals k times t minus t0, and what we'll get is 1 over t minus t0 dt over t minus t0 equals a dt. And this is one that we know how to solve. I'm just going to write this as the natural log t minus t0, kind of ignoring the absolute value part, equals kt plus some constant. And I'll write it as, we'll use the uppercase C for something later. Exponentiate both sides. We get t minus t0 is equal to e to the kt plus c. And so t is equal to e to t plus c plus t0. Now this plus c right here, e to the c is just a constant, so we'll write c k plus 0. I didn't make any mistakes, did I? Okay, that's a homework exercise. Make sure I didn't make mistakes. Okay, let's move on to another example. Y prime is equal to 2xy. And give this one a shot yourself. So this is a good first example to try out. So I'll give you a minute or two to try this out, and we'll work through it together. Anybody got there yet?
I have that y is equal c e to the x squared.
That sounds about right. I think that's right. I haven't worked it out in my notes yet. That's why I'm saying there might be a mistake. So let's
Okay.
work it out together and see if we get
Okay.
this. Okay. So just as a preliminary step, I'm writing this like this for the sake of my own not having to think about it too. Well, let's first of all get the stationary solution. We'll get y is equal. Now I think that gets included in our solution as well. Yeah, if we have y is equal to 0, then it just stays the same forever, no matter what x is. So we can rewrite this dy over y is equal to 2dx. We'll take the antiderivative of both sides. So I get natural log absolute value of y is equal to x squared plus c. Get the absolute value by exponentiating. Absolute value of y is e to the x squared plus c. And convincing myself that it's okay for me to drop the absolute value. E to anything is always positive. So we'll avoid the temptation. Write like this. And then I'll just write it. I'm using the same capital C, but C just stands for an arbitrary constant. So it's arbitrary, and I can take the natural log of it. It's still arbitrary. And I get this. And so I guess we do have to make an assumption here, which is that, oh no, we're totally fine. Okay. So this is our general solution. which, Sydney, I believe is what you said. Okay. Makes me feel better about my ability to do calculus. And the stationary solution here just corresponds to the situation where c is equal to 0. Okay. Let's try a more difficult. Actually, how much time do we have? Okay, we got time for 2. So let's say y prime is equal to e to the x plus y. We agreed this was a separable ODE earlier, so let's see if we can figure out what it is. Go ahead and write the first step. So I get for this the minus y dy e to the x. Yeah. I think that's how we start. Anybody have any ideas on this one? I haven't gone any further, so I don't know how it works.
I got y is e to the x plus c.
Let's try this out then. So integrating both sides, I get minus to the minus y, and on this side I get the x plus c. What I'm attempting to do is solve for y. So I think we're going to get here is let's just move that minus to the minus to the x, replacing c with its negative, and then take the natural log of both sides. What do we get? Minus y is equal to natural log of minus e to the x plus c. I believe at this point there's nothing that we can do to simplify this natural log because we've got this additional constant. But we can move the minus for the other side and get minus natural plus c. Does this seem reasonable? If we had a picture of the slope field, we might be able to say that this is a reasonable solution or not. So barring the possibility that I've made some mistakes here, I think this is the general solution to this. Does that seem right, Tyler? All right, so maybe this is not a particularly exciting one. Now I can say that we don't get a stationary solution for this one. So that's one interesting thing about it. Okay, maybe this one is a little more. Maybe this one's a little more interesting. Let's try y prime is equal to 1 plus, see how much time do we have? About 5 minutes. Let's try this example that we talked about before. I think this one does work out nicely, but it requires remembering something from maybe calc. I'll actually start this one. On the right-hand side, fairly simple integral, right? Just integral. Does anybody remember what the left-hand side is?
Would it be the arctangent of y?
Yes, thank you. I'll say that I probably wouldn't have remembered that if I hadn't looked it up this morning before class. So actually, that's one I should remember. That's really a useful one. So on the right-hand side, we'll have arctangent, which I'll write as atan y. And on this side, we'll have x plus x cubed over 3 plus some constant. And in this case, solving for y is actually pretty easy. We just take the tangent of both sides. So we get y is equal to tangent of x plus cubed over 3 plus c. Interesting. We could maybe look at the slope field of that too and see what that looks like. Maybe that'll be something for another time. Okay, let's try one. Let me do one. I'll just do this one myself, sort of in the time that we have left. Y prime is equal to minus x over y. I'm going to write this as dy dx. And what we get here is y dy is equal to minus x dx. I'll integrate both of these, and I'll get y squared over 2 is equal to minus x squared over 2 plus c. No, let's just write c. Okay, so what's going on here? If I rewrite this slightly, what I get is x squared over 2 plus y squared over 2 is equal to c, or x squared plus y squared is equal to 2c. And you'll immediately recognize this. This is the equation. This is just circle with radius square root of 2c. Now, one thing to notice is that for negative values of c, we don't get a solution, a real valued solution for our function. We could possibly get a complex valued solution, but we're not talking about that at this point. So if we solve for y in this, well, we get our semicircles. So either the top half of a semicircle, or so that would be the top square root, the positive square root, or the negative square root. So when we take the square root of the y part, either that gives us the positive one, so above the x-axis, or the negative one below the y. And we'll choose for our solution. So that would be the general solution. For a particular solution, we would choose if it was the top half or the bottom half, based on what our initial condition was. So if the initial condition was a positive y, we would choose the top half. And if it was a negative y, we would choose the bottom half. Okay. I think that's it for today. Oh, I've gone 2 minutes over. I'm sorry. I'll stick around for questions. Otherwise, I will see you tomorrow.